All right, well, welcome to Chapter 9, which is a big, scary-looking word called stoichiometry. And don't worry about it, because even though it's big, we break it down into its original parts, and it simply means elements measure. So it just means we're measuring elements, but we'll get to that stuff in a little bit. Let's start off with something a little more approachable. I want to show you a picture of one of my favorite toys to play with when I was a kid. All right, you guys have all known me for a few months now, right? And you know that I am a total gearhead, and that means that I love anything to do with cars. And one of my favorite things to play with when I was a kid was something called automoblocks. And they look kind of boring if you look at them, right off the bat, they look kind of stupid. But check out what you can do with them. See this green one right here? This kind of truck-looking thing? Check this out. You could disassemble this thing as far as you wanted. And when you got it all disassembled, you could put it back together however you wanted. And it didn't have to look just like this picture. You could put it back together any way that you wanted. I wanted to use this as an example for stoichiometry because this is a pretty good representation of a molecule, where if we looked at some fancy-looking molecule, like the one we remember so well from last year, this is called cellulose, and it looks like a big scary molecule, but all we really need to worry about is that there are 6 carbons, 12 hydrogens, and 6 oxygen atoms in one of these molecules. It's just like this. And we could break this down into something pretty similar. We could say that if you wanted to build one of these vehicles, you need one front part. That's this guy right here. You need a middle part. You need the back part, this guy right here. We could say, we could say one back. And we also need 4 wheels. And we could keep going and break this down into quite a lot, but this is one of these. Just like all of these is one of these. And so if you wanted to build, for example, say 2 molecules of this cellulose stuff, you would need 12 carbons, and you would need 24 hydrogens, and you would need 12 oxygens. Just like if you wanted to build 2 of one of these, you'd need 2 of the front parts, and 2 of the middle parts, and 2 of the back end parts, and 8 wheels. And so you know exactly how much of each of these you need to build as many of them as you want. That is all stoichiometry is. Let's say that you wanted to write an equation for how to assemble one of these. It might end up looking like this. So if we were going to write this equation, we might say that you need one front, you need one middle, and you need this bed section. Sorry, I couldn't find a color picture of it. And the final thing that you need is 4 wheels. So you've got the basic recipe for building one of these. If you wanted to make 2 of these, you'd need twice as many of all this other stuff, meaning you'd need 2 front end sections, 2 middle sections, 2 back end sections, and not 4 but 8 wheels total. That's stoichiometry. All right? We're going to flip it around and do it with an equation, and I'll show you how it works, and it's really simple. All right, here's a real simple equation. This is aluminum, and this is oxygen gas. And when we combine them, we get something called aluminum oxide, which is an ore, and we're not going to really worry about what its other name is. We'll just call it aluminum oxide. What this formula tells us is that we're going to take 4 atoms of aluminum, and they're going to look like this. We're going to combine these 4 atoms of aluminum with 3 molecules of oxygen gas, and that's going to look like this. And when we're done combining these 4 atoms of aluminum with these 3 molecules of oxygen gas, we're going to get 2 molecules of aluminum oxide, and that's going to look like this. And if you count them up, you'll see that everybody is present and accounted for. There should be 4 aluminums, then there they are, 1, 2, 3, 4. There should be 6 oxygens, and there they are, 1, 2, 3, 4, 5, 6. Okay, sorry. And so that works. This is what stoichiometry asks, and here is a perfectly good question you can expect me to ask you. And that question looks like this. If you want to make 6 molecules of this stuff, how many atoms of this stuff would you need? Now, some of you can look right at this and say, well, this equation tells us how to make 2 of these. If we want to make 3 times as many, we're going to need to multiply this guy by 3 as well. And that means we would need 12 atoms of aluminum. But some of us don't quite see it that way. So I'm going to show you how we do it. And let's remember that when we're looking at this balanced equation, these guys here, these big numbers here, these are called coefficients. And they tell us not just how many atoms, but how many moles. So we could rephrase this equation. We could say that it's not only requiring 4 atoms of aluminum, 3 molecules of oxygen to make 2 molecules of aluminum oxide. It's also moles. It's also saying that if we had 4 moles of aluminum and 3 moles of oxygen gas, we could make 2 moles of aluminum oxide. Let's try this, how we're going to do it, a lot more simply than that. So let's take this question. If you want to make 6 moles of aluminum oxide, how many 6 molecules of aluminum oxide, how many atoms of aluminum would you need? Let's replace those words, molecules and atoms, with moles, because it makes it way simpler. And we know our balanced equation. We know that our balanced equation already tells us the ratio of moles. It says that if you react 4 moles of aluminum with 3 moles of oxygen gas, you get 2 moles of aluminum oxide. So, how many moles of aluminum would you need to make 6 moles of aluminum oxide? So, here is our old buddy, the conversion factor. We're going to go from what we know, which is in this case is moles of aluminum oxide, to moles of aluminum. We know that the ratio from the equation tells us that the ratio of aluminum to aluminum oxide is 4:2. I got that right from the balanced equation. We are putting moles of aluminum oxide on the bottom because that's where we're starting. So notice that this unit here and this unit here are always the same. Okay? This unit up here is what we are trying to find, so it goes on the top. This one and this one are always the same. Okay? All we need to do is plug in our ratios from the balanced equation. 4 moles of aluminum, 2 moles of aluminum oxide. We're going to take our calculator, we're going to multiply across the top, and we're going to divide by the bottom, and that will give us our answer. So let's bust out our calculator. I have mine. So we're going to say, let's turn it on first. We're going to say 6 times 4. That answer divided by 2. And this tells us that if we want to make 6 moles of aluminum oxide, we need 12 moles of aluminum. And that is all that you do. All right? So all you need is the balanced equation and where to plug stuff in. Let's try one more quick one. So this equation tells us that you need 3 moles of hydrogen gas to react with how many moles? If there's nothing there, it's a 1, we don't write it, to produce 2 moles of this NH3 stuff. So here's a question that you can expect me to ask you. How many moles of NH3 could you make from 15 moles of H2? Now, there are some of you that are looking at this and saying that if you're using 15 moles of H2, that's 5 times as many, and that'll give you 5 times as much NH3, and the answer should be 10. I don't do it that way. I'm going to set this up the way we've been doing it. We're going to ask how many moles of NH3 are the equivalent of 15 moles of H2. All right? And let's remember, keep this simple. The first conversion factor that goes on the bottom here should always be the same as the conversion factor that's on the top, moles of H2. So that's going to go right here. We'll say moles of H2 is going to go on the bottom. And the final conversion factor should always be the same as the one you're starting with, because that's what you're trying to find, right? So we're going to say moles of NH3. All you need is the equation to tell you what the ratio is, and that's 2 moles of NH3 and 3 moles of H2. I got them right from here, 2 moles of NH3 and 3 moles of H2. And all you need is your fancy calculator. So I'll bust out mine. What we're going to do is we're going to multiply across the top. And we're going to divide by the bottom, and that'll give us our answer right here. So we're going to say, let's turn this on. Should have had this on before we started. Let's say 15 times 2 divided by 3. How many? 10 moles of NH3. And that's all you do, ladies and gentlemen. So I'd like you to take this for a spin. All right?